I'm going to shift gears a little bit. I was supposed to be first to set the stage, but airplane schedules made it that I just got here. I have exactly one slide, and no more. And I did this on the plane because I was going to go with none, but I thought I would leave you with something to grab onto. So let me set the stage, which picks up on my comment before. Just how much energy do we use now? Well, if you take our energy meter globally and figure out all the joules we use in a year of oil, gas, coal, electricity, and everything combined, on average, it's like running 15 trillion watts. It's 16 actually, but it's 15 trillion watts is what the world's energy meter reads every day. It's been growing. Most projections show that from a combination of economic growth and population growth, if unmitigated, that would triple within our lifetimes. By 2050, it would be 40 or 50 trillion watts. But the IPCC and everybody else builds in heroic amounts of energy efficiency, saving as much energy as all the energy we consume today combined. And that holds it to 30 trillion watts. If you doubled it again, you'd get down to 15 trillion watts. So if you saved as much energy as all the energy we consume today combined twice, you would hold energy demand constant. That's better than the best IPCC scenario builds in. But let me give you that. Let me say that demand is held, that has never been done in human history, constant for a decade. And it's only 15 trillion watts for the rest of our lifetimes. Well, what does that mean for climate? We have to remember that cutting emissions is not the same as cutting concentrations in the air. The concentrations are like your mortgage, not your credit card spending. Every time you emit an ounce or a molecule or something of CO2, half of it stays into the air and half of it partitions into the oceans and the land. We know that. We know the accounting. The exact number is 60%. All right? But the fate of that is that it lasts for, I'm going a little bit out of order, I'll get to the exact numbers, but it lasts for an incredibly long time. That means that the only way to stabilize concentrations at whatever level you pick, 2 degrees C, 450 ppm, or whatever number, is to have zero emissions. Because if you keep emitting at any level, you keep building up CO2. If you cut down the emissions rate to half of what it is now, that would buy you 10 more years before you reached a certain concentration, because you're still building up your credit card debt on your mortgage just a little bit more slowly. Okay? How much is 15 trillion watts? Let's suppose we tried, after holding efficiency to double what we currently consume, some incredibly optimistic thing, we hold demand constant, and we want to get it all from zero carbon energy. Well, a nuclear power plant's 1 billion watts. There are 16,046 days between now and 2050, I calculated it. That means you have to build a new nuclear power plant every single day between now and 2050 if you want to get there that way. If you don't do that, and you want to do it from solar, you have to build 1 million solar roofs somewhere in the world every single day from now until 2050. We're proud in California. We have a goal of 1 million solar roofs in our state in whatever the year is. You have to do not in 10 years, you have to do 1 million roofs every single day. And that's assuming that you had efficiency already built in at twice what current total demand is. As I said, this takes an impossible problem and makes it almost improbably hard, but not impossible. Okay? Now let me go further. What do we know about CO2 concentrations and climate change of the so-called 2 degrees? 2 degrees is a code word for what we estimate to be a level of concentration of 450 parts per million. But actually, nobody knows that if you get to 450 parts per million, what the temperature will be. That comes out of climate models, of the average of averages of models that nobody has a way to calibrate. Okay? So we can't control temperature. We can only control what we can control, which is human-based carbon dioxide emissions, and then roll the dice as to what the temperature will be. It could be lower, it could be higher. There could be nonlinear effects when, as the sea ice starts to continue to melt and the permafrost releases more CO2, there is absolutely no guarantee of anything to do with regulating temperatures based on regulating CO2. So that code word of 2 degrees C from Paris and the IPCC, I think, is a very misleading issue because we have no way to control temperatures. We can only set a budget on the total amount of carbon we emit to control a concentration and then hope that it's not very bad. And there will be winners and losers. Canada might end up growing much more corn. We would export corn from Canada, and would the United States sue Canada for loss of revenue? We have no idea. Paris actually did not have any mechanism in it of actually monitoring who's emitting CO2. It's all based on declarations every 5 years. So what happens if 10 years from now, China says, we cut our emissions because we said so? Well, what do you do? Nobody knows. Okay. How long does CO2 last in the air? If we went to 450 or 550 and then cold turkey stopped and never emitted another ounce of CO2 again, there are 2 time constants. The CO2 in the air equilibrates with the oceans, the near-surface oceans and then the deep oceans. On average, a good number is that it would take 3,000 years, 3,000 to 5,000 years, for carbon dioxide levels to come back down to where we got them from our parents. In other words, in the next 30 years, we're going to be changing the chemistry of our planet for a timescale comparable to recorded human history. That's just the air. The oceans take a lot longer. CO2 in the oceans from volcanic eruptions, we understand ocean acidification, will recover. We'll get back that coral that's 90% bleached in the Great Barrier Reef, where I just flew back from a wonderful vacation in Heron Island, the southernmost part of the reef, because as you probably know, in the warm waters in the northern part, 90% was bleached, and the worst bleaching on record due to warm temperatures and ocean acidification from the CO2 that dissolved. If it gets another 2 or 3 years of that, it probably won't ever recover. It might recover now in 10 years. I was in the southern part on purpose because my colleague from Carnegie Institution had told me, who studies coral reef bleaching, to stay south because I wasn't going to see any coral alive in my lifetime anymore in the north. It's probably right. So it takes 3,000 years to undo what we will do in the air, and it takes over 1 million years to undo what we're going to do in the oceans. Okay? So why doesn't somebody ever tell the public these numbers? This is not about what we know. It's about what we don't know and doing an experiment that we get to do exactly once. Now, let me go further. 50% is less than 100%. I'm going to turn now to how you would do this. Why do I say that? Because there are two big energy gaps. We'll talk all in the rest of today about what I call tactics, very important tactics of how do we bring on more solar and how do we support economic growth while bringing on clean energy and carbon tax versus cap and trade. But I'm going to get above those weeds into a 40,000 foot level here. I think that it's fair to say that reasonable analysis shows we do not have all the technology we need. We need more than political will. This is misleading to think that if we just hit a gavel and just have a climate tax that we're going to be able to plug everybody in whenever we want to for an affordable way in the developing and developed world. We can get about half the way there. For instance, there are two big gaps that every study from the National Academy of Sciences, from the California Energy Future Study that I've been on, identifies that we just can't do affordably today no matter what we think. One is we have no way to store massive quantities of electricity at grid scale, and the more wind and solar and intermittent sources you build, the more storage becomes the long pole in the tent. Edison figured this out in 1931 in a quote to Henry Ford that he said, we can't store electricity, and until we figure it out, we're like Prometheus and baboons. I can show you the quote. You can find it on Wikipedia, but it's with us nearly a century later. We still can't store massive quantities of electricity in an affordable way. The other half is that there ain't no such thing as a plug-in hybrid airplane. Right? Why is this important? It's important because if you look at global transportation and you look at the fraction of global transportation that just can't be electrified, heavy-duty trucks, ships, and aircraft, that's 40% of all transportation fuel demand now. And it's only going to grow. Most projections show that will double. Well, if 40% doubles and you electrified every single or hydrogen, every light-duty vehicle, and you double global transportation to support global commerce, you're back to where you started. So we have to find a way to make carbon neutral, high energy density liquid transportation fuels for that 40% that can't be electrified. It might be biofuels, it might be some artificial way. We've got to find a way to make carbon neutral fuels to keep our ships, heavy duty trucks, and aircraft running. And we've also got to find a way to store massive quantities of electricity, or no matter what we do, my favorite phrase is, he that cannot store shall not have power after 4. All right? I mean, you don't need to get into the weeds with economics to understand just the practicalities of those two statements. Okay. Now let me go a little further into numbers. 10 minutes and an hour. Well, what do I mean by that? Well, people say batteries will get better, and we'll be able to build enough batteries. You'll never build battery-powered aircraft like the 787 I was on with range. Why? Because the energy density in the best battery is 200 watt-hours in a kilogram. The energy density in gasoline is 12,000 watt-hours in a kilogram. You don't need to know anything more than those numbers to understand why we'll be range challenged in light-duty vehicles and why we're never going to make a plug-in hybrid Dreamliner. Okay? That means you've got to find a way to do what a battery can't do and do what chemical bonds do, which is make chemical fuels, which is where nature figured out most of our energy is stored anyway on our planet. It's stored in the chemical bonds of oil, coal, and gas for hundreds of millennia. Well, we got to do that if we're going to make those things both happen. Less than 10 minutes, less than an hour. All the batteries ever made in human history combined would power the United States for 7 minutes. Okay? Let's suppose that you electrified every single light-duty vehicle in our country, 150 million fully Tesla'd cars, and you had one night when, of course, the sun doesn't shine and the wind doesn't blow. How much vehicle-to-grid electricity would you be able to produce by plugging in every one of those 150 million vehicles? You'd power our country for less than an hour. That's it. Then you'd run out of juice, and then you couldn't turn on the lights. Batteries just do not have the energy density that we are used to storing in chemical fuels, and the only way we store electricity on the grid now is in natural gas, in the chemical bonds that we burn in a turbine whenever the sun goes out and the wind goes out. And that's the way we back it up now. But the emissions from that alone, if we did that, would be enough to still kick us over the 450 ppm level. This is the difference between slowing it down and getting to zero. Zero is zero. It's not a half. Okay? Let me go a little further. And then I'm going to close with my numbers, and we'll open this all up for discussion. Yeah. No, look, there are solutions. Okay, look. All of this is on my so-called realistic gloom and doom. You can get this all through my website. I've been giving these kind of realistic energy talks, and I did it at the 25th anniversary of the Berlin Wall. I did it in a TED-style talk. I've done it in Big Think. I've done it over the internet. I've done it in Congress. I've done it to everybody who will listen. So you got the short version here. But it does say that the way to get us through this is through R&D, through technology, to give us better options than the ones that we have now. Because no carbon tax or price signals is going to make solar cheap enough to give us electricity at night, right? So we've got to combine the ability to do the things we know how to do now and lower the cost of wind and solar and nuclear and all the clean energy options we have. But we've also got to be doing R&D to bridge these two gaps of massive electricity storage and this carbon-neutral transportation fuel. I think about it as building a bridge across the Grand Canyon, just building it so that you have enough ability and time that when you get to that point, you can cross. You're not going to do those things now, but if you don't do them, you can't get to zero. And zero is the only mathematically allowed goal that stabilizes the climate. And if you don't do that R&D in the next 10 or 15 years, because it takes so long to bring energy technology up, we won't have it in time. Now, what do? The last number, 120,000 terawatts. That's how much energy we get from the sun. More energy from the sun hits the Earth in 1 hour than all the energy consumed on our planet in an entire year. Nothing else comes close. Not even a factor of 100 close. The wind is 0.5% of the solar because the winds are driven by thermal gradients from pressure gradients of the sun. And on and on. Everything else is small potatoes. Now, that doesn't mean that we couldn't build an energy system by combining wind and solar and other things. It does mean that, look, we're going to run our planet from the biggest energy source we have sometime, because that's the only logical thing, and we're going to store it in the most dense form we know to mankind, which is the nucleus of an atom or chemical bonds. So since that's inevitable, we might as well do it sooner rather than later before we run out of time. And what I work on is a technology that is really at a small scale now that we can't give costs to, that I'm happy to talk about at length anytime you want, but it is what we call artificial photosynthesis. It's inspired by what a plant does. It directly takes sunlight and makes chemical fuel. It doesn't make electricity first. It just spits out chemical fuel that solves the storage problem, that could be used for transportation to solve the transportation problem, to solve the grid scale electricity problem within our existing infrastructure. Now, this is risky, But this is one of the things in a portfolio that I think we should be doing in order to find a way to build those bridges by the time we need them to get to zero. It's not the thing that we should place all our eggs in one basket today to do by any means, but it's an example of the kind of things that R&D could do that would help us get to this goal, and that's the last number I have.